welcome everyone. We're happy that we're all together again. In the previous tutorial, we ended with selecting the HVAC machine that will feed the zones we have from the mechanical equipment tab here. But indeed, those types that we have selected from are not all the types that we can use from, as we have some other devices that we can use. So to access more extra types of the HVAC devices, we can go to the System tab and then to the Mechanical Equipment, and after that we press on Load Family. So we need now to load some families or a family that we can use as an HVAC device. And for that, we will go to the Revit 2017 and then go to the libraries and then the US metric. This is because we are working according to the purchase units. And after that, we select the file that is called the mechanical, as the mechanical file includes the mechanical equipments, and then MEP, which stands for mechanical, electrical, plumbing. And after that, as we are working now on the air side, as the ducts has the air flowing through it, so we need now an air side component. And for that, we'll select that air side components. And as you see, we have here different types represented in different files. Here, the air conditioners, the air handling units, the air terminals, the coils, the energy recovery, the fans and the blowers, and so on. Also, we have the terminal units, and this is our target now, as we need a unit that supplies us with the air we need. So we will select the terminal units, and here we have many templates or many families. Those for the fan coil units, for example, the ceiling ducted, it's hanging on the ceiling, and there are some ducts that going out of it to feed the zone, and the horizontal pull drive, and the direct expansion one, and also many types. When we go down here, we will find that we have many versions according to the different mechanical structure and the different technologies. But when going down, we'll find also we have the vertical air volume boxes, not only the fan coil units. So this is a vertical air volume box for the outlet plenum, which means that it's hanging on the suspended ceiling or on the plenum. And this is the alpha structure, and this is the T structure, this is the transition, this is the Y structure, and the bypass one, and the double duct one. So all of those are some different mechanical structures. And for example, we can use this vertical air volume unit with bypass, and then we press on open, so we will select that type to work on it. And after capturing the family we need now to select it, so we will go to that tab here and select the family that we have just loaded. So the family that we have just loaded is this one, vertical air volume with bypass unit. We select it, and here we can insert it. So when I insert it here, for example, we'll find that we have the same warning that we faced before. The vertical air volume box doesn't appear. This is because the offset level is 0, so we need to make it at an offset level that equals it to P in the range of that ceiling or in the margin of that plenum. And for that, we will make it, for example, to P 3200 millimeter. And now when inserting it, we will find that exactly it appears. So I'll insert it here and then press escape. And that's it. Here we can express it in the 3D form when accessing it. And then press on that selection box. And now let's zoom in a little bit. So let's say the vertical air volume box we have, it has an output. This is its output, and it has a rectangle cross-sectional area, and this is its input, and it has a circular cross-sectional area, which means that this side will be hanged with a circular shaped duct, and this side will be hanged with a rectangular shaped duct. So it receives the air from its input, then it controls the amount that will flow out of it, as it has some dampers. This is because it's a vertical air volume box, so the dampers control the amount of air flowing through it, and then it goes forward through the output to feed the branched ducts and to feed the zone we have. Very good. Now let's close that tab, and then this is the vertical air volume box we have in the 2D form, and our aim now is to connect it or to make it to feed our zones that we have with the air terminals. So if you remember, we have made the air terminals design on the previous tutorial for that room and that one and that one and that one. So I can paste the air terminals again at that ceiling. So I have copied them and I can paste them here. Here, those are the air terminals we have, and our target now is to make the vertical air volume to feed those air terminals or to feed those zones. But as we learned before, each zone is fed separately by a separate device, which means that we have those two spaces which represent this one zone. So those two spaces will be fed by that device or that variable air volume, and those two spaces here will be fed by another variable air volume. This is because those two spaces we consider them before to be a zone, and those two spaces we consider them to be a different zone. And now the first thing we need to do is to specify the position of the variable air volume. So we can select it here and we can move it up here to make that position, for example. And as you see, as we mentioned before, this is its output and this is its input. So we need its output to be in front of the air terminals we have. This is because the output will have a duct and this duct will be connected to those air terminals. And to do so, we easily select it and then we rotate it. So to rotate it, we usually press on that rotate command here, and then it asks us to specify the first line of the angle. So we specify that line and then specify the second line of the angle. So we need it to be rotated with an angle of minus 90 degrees. This is to make its output here in the front of the west direction. So to do so, we will rotate it with an angle of 90 degrees, but clockwise, not anti-clockwise. So we select that line here. And that's it. And now we can make it to P down a little bit by pressing the shift and the down arrow. Very good. Now what we need to do is to go with the duct out of this particle air volume, and to make a duct or to connect its output with a duct, we easily press on that box here. So when pressing in that box, you can see we have a duct that is extended with us to that direction. So we can make it to P until this point here. This is because we need to feed those two air terminals from that main duct. And then we press escape, and after that we will make another duct, and that duct will start from that point and it will end at that point. And after that we will make another duct, so we go to the system again and then duct, and that duct will start from that point and it will end at that point. But you can note here there is an error, as we cannot connect this branched duct with this air terminal. So we can expand that error and see it, and here it tells us that the vertical height between the branched duct and the air terminal is not sufficient to connect between the branched duct and the air terminal. And this is because if we need to connect the branched duct to the air terminal, we use an elbow, so that elbow must have a specific radius, as we learned before. But when the vertical distance is small, the elbow cannot be installed, as the elbow needs a larger vertical distance to be curved, or to take its curved shape, or to take its sufficient curved shape. And to understand what's happening, well, we can see it from the elevation side of view. So we go down and select that east direction, for example. And here, as you see, this is the air terminal that we are working on, and this is the branched duct, and this is the main duct here. So that's the main duct, that's the branched duct that we need to connect to our air terminal. So you can see the air terminal is very close to the branched duct, and for that we need to increase the distance between the air terminal and the duct. And to do so, we can cancel that error, and then we can select that air terminal. So that's the air terminal that we have, and go to its properties. So you can find that its offset distance is 2800. So it's a larger offset distance, which makes the distance between the duct and the air terminal is very small. And for that, we will decrease it to be, for example, 2600. And you see it has gone down. So we go back to the plan view. Here we go up and select the ceiling, and after that we can repeat what we have done again. So we go to the system and insert a duct, and from that point to that point here, and that's it. Congratulations, we have managed exactly to connect the duct or our main duct with the branched duct. And now let's see that again in the elevation side of view. So we're going down again to the elevation. We will find that we have a sufficient distance now to make the elbow, as we said, or for its elbow to take its required curved shape or its required radius. So the elbow is connected to the air terminals with no problems. But what I need you to know is that until now, all what we have made is only for the illustration purpose, as we are not making a precise design at all. So we are supposing now some examples only for the designing idea to reach you. But after finishing all the design steps, we will jump to the complete project at which we will make some accurate designs with some very precise dimensions and well-organized plans for all of the project steps. For example, we will make the ducts and the air terminals require dimensioning calculations, but for now we're just inserting some random ducts to see how can we make it. Alright, now let's go back. Here what we did on that air terminal will be done on all the air terminals we have, so we can select all the air terminals here, that one, and that one, and that one, and that one, and now we will make this offset distance to be 2600 instead of 2800. Here let's change it to be 2600. Now we will connect that air terminal with that duct, and for that we will press on duct again, and then save. We don't need to save now, and start from that point to that point, and that's it. But we delete that extended part of that duct, as the duct will be ended at that position. So there is no forward air terminals, or there is no forward rooms or zones for that main duct to feed. So we delete that forward extension, and for that we will extend the column that we have learned before, which is the trim extend. So we will go to the modify tab, and then choose the option which is trim extend to corner. So we will make an elbow shape between that duct and that duct. So we will select that trim extend command, and then we will select that first duct and this second duct to be the second one. And that's it. Here we have managed to make it a PUT design with a curved elbow here, so we don't need any extensions or any parts that are not important for us. So that elbow shape is more efficient as it produces the less disturbance and the less losses, as we said before, in the air during its flow through it. So that's about the first doing that we have, and we have connected it with its vertical air box. Now for the second zone, here this is the second zone that consists of this room and this room. So we can copy that variable air volume box. Here we select it and then press and copy. And now start from that point and insert that at that point, for example. And then we need to rotate it. This is because its output is in the front of the west direction, but the air terminals here are at the east direction. So after selecting it, we will rotate it. Here to rotate it, we can choose that rotate command, but we have a very simple way for doing so, which is to press easily on the space on your keyboard. So when I press on the space, it's rotating easily as we need. That's what we need. Its output is in the front of our zone. And then we will make another duct by the same way by pressing on that box. So the duct is moving with us. We can end at that point and then press escape. And then what we will do easily is to connect that main duct with a branched duct to that air terminal. So we go to the system tab and then duct again, and start from that point and end at that point. And that's it. Here we will do another one from that point here to that point, and then a third one. So this duct will continue to feed that air terminal, and for that we will start from that point here to that duct, and that's it. And what we did before on that elbow shape here will be done on that elbow shape here, as we don't need that extension. So we will go to the modify tab and trim extend command, and then select that duct and that second one, and that's it. Here we have made it to be with an elbow shape that is most suitable for the design. Also, we can see that design or that full design in the 3D shape to make more sense for you. So we can select it, and then we press on that selection box. So as you see, this is our system. Here, this is the second variable air volume that is connected to that zone. That zone consists of 3 air terminals, those two ones and that one. And here, that's the first vertical air volume. Also, it's connected to those 2 air terminals. Very good. So that's about this step of our design. And on the next tutorial, we will continue the next tracks for our design. Hope that's it right now. Thank you for watching, and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial, we have made that simple design on the duct system, and now let's continue the steps related to the design. Now let's copy that variable air volume, for example, to make some operation on it. So we press and copy, and start from that point and make the insertion point to be, for example, that point here. So we insert the vertical air volume box at that point, and then we press on escape. The first thing we need to do is to make a duct out of this vertical air volume box. So what we did on the previous tutorial is to press on that box here, and the duct will be extended without, as you see here, by that way. But we have also another way, which is to go to that box. And you see we have that small square here, so when we press into it and then press the right click, you can see we can draw a duct. So this is the second way by which we can draw a duct. So the first way from that box here easily, or we press on that box and right click and draw duct. That's it. Also, what we want to say is that design that we have made on the previous tutorial, by making that vertical air volume at that position and to go with the duct from that direction, not for that direction, and also to make that second vertical air volume at that position, not making it at that position, for example, or at that position, and making the ducts to go through that way. So that design is merely done according to your point of view and your experience. For example, that is the design that I have made, but another designer may change the design and put the vertical air volumes and the duct routing or the duct paths at other positions. But you must also know when you make the design that there are some design standards or some tricks that make the design a good one or an efficient one. For example, you should make the design that consumes the least amount of the ducts, so you are saving the cost now at that time, as you are reducing the ducts used, so you are reducing the materials that you are using, and then you make the design a more economic one. For example, if I take that vertical air volume box and I put it at that position, I may consume a less amount of the ducts. Also, the second note is that you should make the routing process to be simple as much as possible. So you need to avoid the complex paths of the ducts and the complex connections. And you do that to make it easier for the ducts to be installed on the real site when constructing the building. And also you need to reduce the installation connections between the main ducts and the branch ducts as much as possible to make it simple for the installation or to make a more simpler design. And also another note is that if you reach at the end of the duct, for example, I can make a duct here. I go to the system and duct and start from that point to that point, for example. So suppose, for example, this duct will be ending at that position, but this duct is an open one, and we need to close that duct. And for that, we go to the duct end here. When selecting it, we will find that we have this option at this tab here, which is to cap the opening ends. So when pressing on it, here you will find that an extension has been done to the duct, which is to close the duct end or to cap it or to make its end a solid one. So that's about the capping operation if you have reached the end of the duct. Also, we can do the same thing by pressing on the duct and right click and then use that option which is to cap open ends. So the duct end here has been capped. Very good. Now let's go to that design, for example. And if we need to take a section from that duct, we usually press on that section tab and then start from that point, for example, to that point. And then we access that section here by pressing the double click on it. So that's the duct we have, but it appears to be a single line here because of the details level is very low, so we can increase it to be fine. And that's it. Here the duct has appeared for us. But if you remember on the previous tutorial, when the vertical distance between the duct and the air terminal was narrow, and in that case we were not able to draw any output to link between that branched duct and that air terminal. And in the practical working, if we are facing like those confusion or those conditions, when the suspended ceiling is a narrow one, so we cannot increase the distance. Here we have increased the distance for the air terminal. This is because we have no specific design to work on. But in some cases, the suspended ceiling height may be a small one that may be, for example, 3 centimeters only. So if we face like those conditions and we cannot install the elbow here like this one, what we will do is to use the flexible duct. So the flexible duct now is used instead of the elbow duct. This is because it's a flexible one, so we can bend it and decrease its size to cope with the narrow available distance. And to use the flexible duct, we easily can delete that duct here or that elbow one and delete that neck and that one And then we go back to our ceiling. So that's our ceiling. And then we can use the flexible duct. So the flexible duct will connect from that point to that point here. And that's it. Now let's see it again from the section that we have. So we go to the section. And that's it. So this is the flexible duct, and we use that because it's a flexible one, so we can decrease its length as we need. Very good. So that's about some important tips related to our design. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will continue our HVAC designing steps. Now, after completing the ducts design inside the ceiling we need to add the insulation specifications for our ducts. And the insulation of any duct has two types, the interior insulation and the exterior insulation. So for the exterior insulation, it's used to insulate the inside air or the supplying air that is going inside the ducts. We need to insulate it from the outside or the surrounding temperature of the outside air or the outside climate. And this is because of the inside airflow is the conditioned air. But if there is a heat exchange between the air inside the duct and the air outside the duct or the surrounding air, at this condition, the supplying air will lose its conditioning temperature. So we need to isolate the outside surface of the metallic duct, and this is by the insulating material. And that outside surface insulation has a standard thickness to be, for example, 25 millimeter, which is about 1 inch. And this is in case of the duct lays inside the building. But if the duct lays outside the building or at the roof of the building, so the insulation thickness at that condition will be the double of the insulation at the inside condition or the interior ducts condition. So at that condition, it will be 50 millimeter instead of 25 millimeter. And this 50 millimeter is about 2 inches. But this is a logical thing to have the interior duct insulation with a lower thickness than the exterior duct insulation. This is because of the temperature outside the building or at the roof of the building will be larger in the summer season, so the heat exchanging process between the duct and the outside air will be a larger one or will be larger than if the duct lays inside the building, as the temperature will be lower, then the heat exchange will be less than the exterior heat exchange. Alright. Now to add an external insulation for the duct, we easily select the duct we have and then press on that add insulation tab. And here this is the standard thickness as we said to be 25 millimeter. But if you are working on another case for another thickness, you can easily change it according to the design you are working on. And also we can change the type of the insulating material itself. So when pressing on edit type here, you will find that we can edit the type of the insulating material from that tab. For example, the deck wrap, that is the standard one, or the fiberglass, or the PVC jacketed fiberglass, and so on. And also we can specify the insulation surface color or its internal material at its internal cross-sectional area. So this is for the exterior insulation. And here press OK, and OK, and OK. But after talking about the exterior insulation of the duct, we have also the second type of the insulation, which is the interior insulation, which is an insulating material that is placed inside the duct itself, not outside the duct. And we use that interior insulation to reduce the air noise inside the duct due to the airflow. As we learned it, because when the air moves through the duct, it makes some collision and some disturbance with the duct surface or the inside surface of the duct, and also the fan itself that it pulls the air inside the duct produces some noise. So we need an insulating material inside the duct itself to reduce that noise inside the duct. And for that we use the inside insulation that is called here the lining. So when pressing an edge, we will find that it has also a standard thickness of 25 millimeter, or we can set it with its value that we have, and its standard type here is the fiberglass, but we can use also the textile one and so on. And after that we press on OK. So we go into the duct itself, we will find that here this is the main surface of the duct, and this is the thickness of the interior insulation, and this is the thickness of the exterior insulation. So we can check that by measuring here from that point to that point. So it's exactly 25 millimeter. This is for the exterior insulation, but from the duct surface to the interior insulation, we can measure it from that point to that point, and it's also 25 millimeters. So that's about the interior insulation and the exterior insulation. But the important note to know is that the exterior insulation is going through the total length of the duct from its beginning to its end. But for the interior insulation, we just install it at a length of 2 meters from the starting of the supplying fan source or from the supplying vertical air volume box, for example. And we install it at the first part only to be at 2 meters, for example. This is because the noise of the air inside the duct will be at its maximum value at the source, which may be the fan coil unit or the vertical air volume, so we need to reduce that noise at that position only. Also, we have another powerful tool into the Revit software, which is called the System Inspector. So if I select that duct, for example, you can see we have this option here, which is the System Inspector, and then we press on Inspection. So by that option, the program tells us about the airflow inside the duct and the specification of that duct. So it tells us, for example, that the airflow inside that duct is 470 liters per second, and its static pressure is about 667.6 Pascal, and its pressure losses, here this is its pressure losses, we can see it's about 591.1 Pascal. But when going there after the first duct, we will find that the airflow has been decreased to 235 liters per second, and the static pressure also has been decreased to 76.5, and its pressure losses also has been decreased to 26.7 Pascal. And this is because there is a branched duct here that has absorbed some of the airflow inside the duct. So when the airflow inside the main duct increases after this first branch, it's logically that we find the airflow to be decreased and its static pressure and its losses. So that's about the main duct. But we have the same thing for the branched duct. Here, for the branched duct, the airflow inside it, we find it to be 235 liters per second, and its static pressure is 76.5, and its pressure losses is 18.1. And also the same thing, if we go to the second section, we have its static pressure, its total airflow, and its total pressure losses. So what the program made to calculate the total value of the airflow inside the main duct is easily to sum each air terminal required airflow. For example, this first air terminal need 235 and the second one need 235. So when we sum them, we will find that it's exactly 470 liters per second. But for example, if we cancel that order and if we go to this air terminal and we go to its properties, and let's decrease its required airflow to be, for example, only 100 liters per second, and then apply, and then make the system inspection again, and make the inspection. So we will find that this air terminal needs 100 liters per second, but this air terminal needs 235 liters per second. So when we see the total liters per second required, it's 335, which means that it's exactly the sum of the two air terminals required CFM. Very good. Now let's cancel the system inspection, and also you can apply it at any system you have at that system or for any complicated system for any design. And now after making the design, we need to check that our design is being done well or there is no faults inside our design. As in some cases, there may be some faults inside some ducts or some disconnected ducts, or for example, there may be some misconnections or some ducts that you didn't put the cap at the end of it. So we need to check all of that to check that there is no problem at our design. And for that, we easily select our system here and then press on show related warnings. So it tells us that we have one warning, and that warning here is related to the duct fitting or at that elbow here. So when we go to the project browser and then go to the installation, for example, we will find that it tells us that this fitting is not a suitable one, or the angle at which we are making our flexible one is not suitable one. Very good. So that's about the warnings that we can have inside our system. And also we have another check which is called the interference check, as it tells us if there is any interference at the ducts we have. For example, two ducts may be overlap, so the program can detect that interference. But for that small system, it may not be a problem problem as we can detect any error with our ease, but this will be a problem for the large systems that have complex details of the ducts and the air terminals. So to do so, or to do that interference check, we easily go to the Collaborate tab and then select that interference check and then press on Run Interference Check. So it tells us about the components that we need to check the interference at which. So we press on All and then press at any one of them. So we need to check all of those elements. And also at this one, we check on all and select all of them and press OK. And here it tells us that we have no interference detected at any component inside our system. Very good. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will continue illustrating these tips and tricks to prepare ourselves for the complete HVAC project implementation. If you remember on the previous tutorial, we worked on that suspended ceiling. And now this tutorial, we will work on the second suspended ceiling, which is this one here. So that one was for the ground floor, and that one that we will work on now is for the first floor. And now we will copy those diffusers here for that down ceiling. Here we will select all of those components as we learned before, and then press on Filter, and check None, and then select only the air terminals, and press Apply, and OK. And then after selecting them, we will press on Copy, and go to the second ceiling on the second floor or the first floor, and then press Paste, and then align to current view exactly as we have learned it before. And after pasting them, let's handle their position. For example, let's make their offset to be 2300 millimeter. And now let's go to the mechanical equipment to load another supplying machine. So we go to the system and then mechanical equipment and load family. And we will go to the same path that we have captured before. But for a short time, I have saved in the favorites. So when I go to the favorites, and if you remember on the previous tutorial, we have selected one, which was the vertical and volume bypass. But for now, we will select another one. So we need to work on some different devices to be familiar with the different devices or the different cases that we can face. So for the illustration purpose, let's choose that one, which is the vertical volume with yellow duct. If we select it and press on Open, and as you see, this is the machine or the vertical volume box that we have selected, and it has some different dimensions here, 5 by 5 inches, 6 by 5, 6 by 6, and so on. So we'll select this default size, and then for its offset, let's make it to be, for example, 2900 millimeter, and that's it. Here we can place it at this position, for example, and then press Escape. Now in accessing it to separate, we'll find that this is its shape. Here, let's see it in the 3 dimensions. As you see, this is the box. We can rotate it a little bit. So this box has the output duct from that position, which has a rectangle cross-sectional area, while it has 2 input ducts here. So this is an input duct, and this is another input duct. So its 2 input has the circular shape, and its output has a rectangle shape. So this means that we will go out forward with a duct to feed the zones we have on the air terminals. Very good. Now let's access it in the 2D form. This is its shape here, and we will go out with a duct from that direction. As we said before, it's up to you to position any component you have. So I have positioned it at that position. You may position it at that position or at that position, for example, and so on. But when you are making the design, you must take into account the required step to end up with an efficient design. Now let's extend that vertical or volume box duct here from that position. Let's make it to end at that position. Also, we can make our mode to be in the shaded form. We can shade it. That's good. But here, as you see, the duct is going out of the box with the same dimensions of the VAV box neck. So this is the VAV box neck, and this is the duct, and they have the same dimensions exactly. But actually, in the practical design, we may need a duct with some different dimensions that is different from the output vertical air volume box neck. And this is because we may calculate the required total cubic feet per minute that is required to feed that zone. So it has a specific value that needs a specific cross-sectional area for the duct. So the cross-sectional area now may be different from the VAV box interface in some cases. And for that, we can delete that duct. Here we select it and delete it. And then we draw the duct with the required dimensions. So duct, and then reduce its width. So instead of 500 millimeter, we can set it, for example, to be 300 millimeter. And then we start from that point and end at that point, for example, and that's it. And as you see, the duct reducer has been generated automatically to fit the two ducts together or to fit the VAV box neck and this duct we have. But also we can do the inverse, which is that we may have a duct output of the VAV box with a larger cross-sectional area than the cross-sectional area of the neck of the VAV box. And for that, we can delete that duct, and then we can delete that reducer also. And after that, we go to the duct again and insert the duct, but at that condition, we can insert it to be with a width of 600 millimeter, and then go out from this point to that point, and at this condition, we have another duct fitting, which fits between this neck of the VAV box and that duct out of it. And you see, this fitting operation is done automatically. But you know, in the practical design, the main duct is larger than the vertical air volume neck, so we don't connect the neck directly on the VAV box, but we go out of the VAV box with a duct that has the same dimensions of the VAV box neck, which goes out of it with a specific length, and then we connect that duct with the main duct that will feed the diffusers we have or that will go out of the VAV box. And to do so, here we delete that duct and then we select the VAV box and we go out of it with a duct. Here we go out of it with a duct that may have this length, for example, and then press escape. You can see this duct has the same length of the VAV box neck, and then we go from that duct with the duct that we need, or the main duct with the main cross-sectional area, which may be, for example, 600 millimeter. So we start from that point and we end, for example, at that point. That's it. And here we do that linking operation because that design reduces the air noise and the disturbance inside the main duct. And also this linking duct enables us to put the inside insulating material inside that part of the duct that is nearer to the vertical air volume box, so we can reduce the noise by that condition as we said before. And also we use that part of the duct with the same dimension, as we may use it to put any controlling element that may be positioned at that position like the dampers, so we are getting the benefit from that linking duct for those reasons. And now suppose we need to connect that VAV box to the air terminals we have. So we have learned that operation on the previous tutorial. Easily we go with a duct out of this main duct, here a branch duct to that air terminal and another branch duct to that air terminal. So we go to the duct and easily we can change the width. So we can make it, for example, to be 300 millimeter and then start from that point to that point here. And that's it. And the same thing for that duct. Here we go to the duct again and the branch duct from that one to that air terminal, and that's it. But you know, there's a more simpler automated way for doing so. So we can make the routing operation by making the duct forward and making those two branches with a fully automated way without your manual design or without your manual extension of the ducts. And for that purpose, let's delete those ducts. Here we can select that one and delete it, and also this one and that part. And also we can delete all the ducts at that part. That's it. And now what we will do is to select that air terminal, for example, and then you see we have this option which is this duct. So when we select it, we will find that this window pops up for you, which tells us that we are going to construct an air system of the supplying type. And that's right, as this type is a supplying one, as the air is going forward from the VAV box to the air terminals. And it asks us for its name, so let's rename it, for example, to PD Auto System. And then it asks us if we need to edit that system, so we check that box here to edit it, and then press OK. Now what we need to do is to add the components that will be included in that system. Here as we have two air terminals, so we add that one, and then we add that one. But to select the VAV box, it's not an ordinary component as it's the supplying unit. And to include it inside the system, we press on that select equipment tab and then we select it easily. So by that way, our system includes that VAV box as a supplying unit and those two air terminals. And after that, we press on finish editing the system. And now to generate the ducts routing automatically, we select that air terminal, for example, and press on the top button on the keyboard. So you can see we have a rectangle dash border around the system we have, and we easily press on that tab, which is to generate the layout. This is for the auto routing, and you can see that's the auto routing operation. This is the path that the program suggests for us. So this is the solution here, or those are the solutions. But you can see we have 5 different solutions. So when we explore them, we will find that this is the first solution to have the main duct starts from that point to go inside that air terminal and then a branched duct from that air terminal to that second air terminal. Now the second solution that the program suggests for us is that one, which is to have a main duct from that point here until that point, and then to have a branched duct to that air terminal and another one to that air terminal. And also we have a third one, which is to have a main duct from that path here and then to have a branched duct to that one and a branched duct to that one. But you can also, when we have this yellow color for the routing operation or for the routing duct, this means that there is a problem in that branch. Also, let's see another one. So this is another suggestion. And this is the fifth suggestion here to have that main duct and that branched duct and that branched duct. Now, for example, let's select that one here, which have an error in the routing operation. So when we select it and press on finish layout, you will see exactly this auto routing operation has some errors. So this is not a right design anyway. Here it's not necessary to use that auto routing, but we suppose it only add another solution that you may have to use. Very good. Now let's press Ctrl Z to go back to the original manual routed duct. Now you may note that when we created the duct, it was created with the default properties on the default offset, for example, or on the default dimensions. But in some cases, we need to set the duct on a specific level and also to have a specific width or generally some specific dimensions, as we may need to make an array of branched ducts, for example. So suppose we have, instead of 2 air terminals, we may have 5 air terminals at that direction, and each of them will be fed by the same branch. So that means that branch will have the same offset of that branch, will have the same offset of the forward branches, and also they will have the same dimensions, as those air terminals may have the same airflow through them. So instead of setting the ducts properties each time on a specific value, we easily can select the duct, for example, and press a right click, and we have that option to create similar. So when we create a similar duct from that point, for example, to that point, here when selecting it, we will find that it has the width of 300 and it has the offset of 2900. And also, if we selected that duct, we will find that exactly it has the same offset of 2900 and its width also is 300. So what we want to say is that select similar option helps us greatly to copy the duct for parts without creating it from scratch each time. Very good. So that's about this tutorial. Hope that's it clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. And this tutorial will continue illustrating the steps related to the duct system design. First of all, you may notice that during our design there are some automated structures that may be automatically made with some assumptions from the software. For example, if I draw a duct here, I go to duct, and then make it from that point to that point. And let's make another duct also, but let's make it now with a width of 100 millimeter only instead of 300 millimeter. So when we make it from that point to that point, you can see there is an automated duct reducer or an automated fitting that has been done to connect between that larger duct and that smaller duct. So that reducer has a specific length and a specific declination angle here, and those specific values are specified by the program by default. Also, if we try to draw another duct, suppose we draw another duct with an elbow shape, here at that point to that point, you can notice we have here an elbow with a specific radius that the program assumed. So we need to know now how the program assumed those values of the automated designs. So those settings of the automated designs can be controlled actually from a tab that is called the routing preferences. And to access that routing preferences tab, we easily select that duct. For example, here we can select any duct like that one, and then we go to edit type, and here you can see this is the routing preferences tab. We can access it. Here you can see all of those are some default values for the auto routing operation of the ducts. Firstly, for the elbow, its default cross-sectional area is the rectangular shape, and when we drag this menu down, we will find that we have some other options. So we may have an elbow with the rectangular shape and its radius to be with the metric standards, and also we may have another elbow with a radius of 1 and another elbow with a radius of 1.5 and another elbow with a radius of 2 and so on. So we can change it to P2 for example, and that means if we draw now an elbow in our design, it will be drawn with a radius of 2. So we have those standards here that we can select from them. Now let's try that. Here I press on OK and then apply and then OK. Now if I draw another duct with the elbow, so I can go to the duct and draw from that point to that point to that point. You can see if I select that elbow now, here exactly its radius is 2. This is because we had to change the auto routing preferences to make the elbow setting with a radius of 2. Very good. But now what about if we need to work on a different elbow with a different radius? As we said, we have the standard radius to P1, 1.5, and 2. But what about if we need to make the radius, for example, that we will work on to be 1.25? Here what we will do is to select the elbow here and then press on edit type. So we will edit now the elbow radius type, and then we will create another template for the elbow. So we will press on duplicate, and now it asks us for the name of that elbow. So we can rename it to P radius equal 1.25 for example, and press OK. So that's the name of the new type we need, or the new template we need for the elbow radius. And here we select its radius exactly as we need. So we can set it to P1.25 and then press OK. And now if we need to set that new radius, which is 1.25, we will go again to the routing preferences. So we select the duct and then edit type and then routing preferences. And now for the elbow, we will select the new one that we have created. And exactly this is the new one that we have created, the new template. We select it, which is 1.25, and then press OK and then apply and then OK. And that's it. Here, if I try to draw another duct by pressing on duct and start from that point to that one, for example, to make an elbow, and here if I selected that elbow radius, we will find that it's exactly 1.25 as we need. So what we want to say is that you can use the default radius, or you can create a new template for the radius or for some other routing preferences as you need. Very good. Now let's go back to our routing preferences. Now the second module we have for the routing preferences is the preferred junction type. So it may be of the T-type or of the tap type. And the difference between them is that for the T-type, there is a separate fixing box that connects the two branches on the two ducts together. While for the tap type, the vertical duct is going directly, or it's installed directly to be interfered with the horizontal duct. And then we have other specification for the junction. So it may be for the rectangular takeoff type, or it may be the rectangular T-type. So all of those are some structures or some mechanical structures that can connect the two ducts together. And after that, we have the cross type. So we may have a cross of the rectangular shape, or we may have none. So we may have no crosses, or we may have the rectangular cross. And that cross type means what will be the fitting type of the intersection between the two ducts in case if we have two ducts intersect with each other. So if we made it to P none, this means there is no fitting between the two ducts. But the other tab, which is the rectangular one, is the one that we use in the practical working a lot, as this cross is a separate piece of duct that is used to connect two intersected ducts together. And to understand the difference between the none type and the cross type wall, we can draw both of them. So if I select it to P none, for example, and I press on OK, and then I press on apply, and then OK, and then I draw a duct. So if I go to duct, and I draw a duct from that point to that point, for example, and then I draw another duct. Here it can be from that point to that point, and press escape. So that's for the non-cross type, but if I try to draw another one, here go to edit type again, and then routing preference, And let's make it to be the rectangular cross standard one and press OK and then apply. Now I drew another duct and another one here to make the cross. As you see, this is the difference between them. Here for the none type, you can see the two ducts exactly intersects together with no junction box that connects the ducts together. While on that type here, we have a separate port, which is this one here. So if I select it, this is a separate port of the cross type that connects those four ducts together. So we can say that those are two ducts that interfered with each other, but those are four ducts that are entering to the four interfaces of that part or that cross part. And we can select them here and show them or express them in the 3D form. So if I go to that selection box, you can see those are the two types. This is a junction box, or it's a cross type that exactly connects the four ducts together. So this is a separate part from those four ducts. While on the other hand, for that type, we have two ducts that interfered with each other with no cross between each of them. Very good. Now let's close that and go to the next routing preference we have. Here the next thing is the transition, which specifies the reducer angle. As we said before, if we try to connect two ducts together that has two different cross-sectional area, so we will need a fitting of the reducer type, and that reducer type will have a declination angle. So this angle may be 15 degree or 30 degree or 45 degree or 60 degree. So if I specify it to be 15 degree, for example, and I press on OK and then apply and then OK, and after that, I can try to draw a duct. And then let's make its width, for example, to be 5,000 and start from that point to that point. And then if I try to draw another duct, but at that time its width may be 300 and then start from that point to that point. And you see, this is the duct reducer we have with an angle of 15 degrees. So if I select it, you'll see its angle is 15 degree. But if I select it here, I can change its angle. So if I go down, I can change it, for example, to be 60 degree. And that's it. You can see the depth reducer length or the fitting length has been decreased greatly. This is because we have increased the angle or the declination angle. And also those values, you can set them from the routing preference as you need to work on the default values that you need. Now let's go back to the routing preferences. Here the next part we have, or the next setting type we have, is the multi-shape transition from rectangular to round. And in that case, we specify the transition angle and its duct shape when we connect a duct with a different duct that has a different shape. So this is in case of we connect two ducts with different shapes. So from the rectangular to round, here we specify the fitting or the reducer angle to be with the same concept: 15, 30, 45, 60, and so on. Also, we have the same thing, but if we need to transfer or if we need to connect the rectangular type to the oval type. So it asks us if we need its length to be the standard or we need it to be void or none. And after that, we have the multi-shape transition, oval to round. So we can select it also to be none or to be the rectangle union standard. And the same concept for the other two routing preferences, you select them as you need. And finally, we have the cap type. So we may have a cap at the end of the duct. This is to be done automatically, or we may have none. This is in case of we need to make the cap ourselves. Very good. So that's about the automated routing preferences that we have, and to set it as you need to start your project with the default values that you need. Hope that's it right now. Thank you for watching and see you next tutorials. Oh, welcome everyone. We're happy that we're all together again. In this tutorial, we will continue exploring the options and the properties that we can use during our HVAC design and the Revit software. Here, as you see, those are some mechanical options that we can use. For example, we can draw a duct, or we can select an air terminal or a mechanical equipment, for example. But for those elements, there are some general settings that we need to set or we need to fix. But to access those settings, we easily press on that tab here, which is the mechanical setting. Here we press an F, and you see the first option is related to the hidden lines, which means, for example, if we put a duct to be overlapped with another duct, the hidden parts of the lower duct will be shown if we select that option, or it may be hidden if we didn't select that option. So if we select it to be hidden, and we press on OK, and then suppose we draw two ducts, so we draw a duct here, by that way, and then we draw another duct. So you see those two ducts intersect with each other, but we need one of them to be overlapped on the other, and for that we will change the offset of one of them. So if I select that one and I change its offset, for example, to decrease it to be, for example, 2600 millimeter, and that's it. Now you see this is the upper duct and its lines of the intersection part is hidden, and this is the down duct and it hides the parts of the upper duct. So we can express it in the 3D form to imagine it full. Here I select this and press on the selection box, and then we can go down to see them all. So you can see we have this is the over duct and this is the down duct. But as we may be setting to hide the lines, so the over duct lines at this intersection area are hide. But on the other hand, if we change it, that option again, so if we made it to draw the hidden lines and press OK, and that's it. Here you can see there are some dashed lines of the over duct, and that's because we have made the hidden lines to appear. Now let's go again. Also, we can change the length of the inside gap line and the outside gap line and the single line. So those are some options related to the style of the hidden parts lines that we may show or we may hide. Now the second group of setting is related to the duct we have. So for the duct, we need to specify some settings like the angle by which we can draw the duct. So if we go to that angle, here we can select it to be any. Here that means for the angle at that condition, we will be able to draw any angle we need during the design. So we have the flexibility to draw the duct with any angle or to go through any direction to draw the duct. While if we select it to be an incremental angle, at that condition the angle we draw will be changed by the resolution of the increment or the decrement. So if we select the increment option, for example, to be 20 degrees, this means we are able only to draw the curved ducts on an angle of 20, 40, 60, and so on. So let's try that by pressing OK and then draw a duct. And let's make its width to be, for example, 100, and then we draw it at this position, for example. And now if we try to draw another duct, so if I try to draw it with an angle of 90 degrees, for example, the duct cannot be drawn with an angle of 90 degrees. This is because we have set the incremental angle to be 20 degrees, so it have drawn with an angle of 100 degrees. This is because it's the nearest angle to the 90 degrees, so it will be from 80 to 100, then from 100 to 120, but we have no option to be with 90 degree, as the 90 degree is between the 80 and the 100. So that's for the incremental angle. And also we can see the third option we have is to set it to be with a specific angle, and by that option we specify some standard angles that we will work on. And we cannot draw a duct with an angle that doesn't exist on those standards. So that's about the options of the angle fitting. But in general, in the standard working, we specify it to be any angle, as all of the installation structures of the ducts can be constructed easily by the technicians in the site of construction. This is for the ducts. While on the other hand, if we go to the pipe setting, at this condition, we should use some specific angles to work on them, not any angle. And this is because the pipes are manufactured with some standard angles that have some limitations. So we must specify the pipe angle exactly as we will use in the real site according to the pipes that we have. So we specify here those standard angles of the pipes. And after that, for the ducts, we have the conversion branch here. And at that conversion module, we need to specify the initial duct type. So if we draw a duct, you see it's drawn automatically with the rectangular shape. But we can change this initial type to be the oval, for example. So if I select that one, I can change it to be the round type. or I can select it again to P for the oval type, for example, and so on. So this is the initial type of the duct that we will draw initially in our design. And then we have also the standard offset that we draw the duct according to it. So it's a standard value as 2750, but we can change it also for any value that we need. This is according to the case that we need, as we need a precise offset with respect to the suspended ceiling or with respect to the other components we have. And also we do the same thing for the branch duct. So those options for the main duct and those options for the branch duct that we extend from the main duct. Also, it asks us for the flexible duct type, as the flexible duct type is a branched one, so we can select it to P, for example, the round one, or we can select it to P now and so on. And then it asks us for the maximum length of the flexible duct that we can use in our project. Pretty good. So that's about the conversion module. And after that, we move to the rectangular duct type. And here we have some standard widths of the rectangular shaped duct that we can use by default. So those are some standard sizes. But if we need to add another specific size that is not available in those sizes, we easily press on that new size tab. And then it asks us for the size that we need to enter. So we may enter a size, for example, of 80 millimeter. And then press OK, and you see the 80 millimeter size has appeared here, so we can select it. Also, we can do the inverse to delete a size. So if I select the 100, for example, I can delete it easily. Here it tells us that the 100 millimeter duct size is exactly used in our project. So if we removed it, it will be removed from our project. I'll press an yes. This is only for an example. But you may notice here we have two columns for each size. The first one is used in the sized list, and by checking that option, this specific size will be included in the sizing list, and if we deselect it, it will not be included in the sizing list. So if I try to deselect this one, for example, 90 and 110, so if I deselect it, they will be disappear, and I press on OK. So if I press on duct, and then we drag down the width list, you see the 90 millimeter width disappear, and also the 110 disappear. This is because we have deselected them. Now let's go back. Here we can select them again. So let's about this column, which is to use those sizes in the list. But on the other hand, the second column here, which is used in sizing, this column will include the checked sizes here and the automatic sizing process. As in some cases, the duct sizing are specified automatically, so the program will select from those sizes here that we have checked in case of any size is selected automatically. But if we deselect any of them also, they will be excluded from the automatic selecting operation of the duct sizes. So that's for the rectangle type, and so on for the rest of the types. We have the oval and the round and so on. And finally, we have the calculations. So the program tells us about the calculation method that it makes the duct sizing according to it. Very good. So that's about the important mechanical settings. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello, welcome everyone. Very happy that we're all together again. In this tutorial, we will continue discussing the nodes and the tools about the duct design that we are facing during our design. First of all, we need to clarify that there may be some critical cases that you may face during your design, and one of those cases is that the height of the suspended ceiling may be smaller than the height of the components that you need to install inside it. For example, if we go to the first floor ceiling, here we take a section of that ceiling, we go to the section and start from that point to that point and then access it. Now let's increase the height of the section. Very good. So this is the suspended ceiling area that we have, or this is the plenum area that we have. And if we need to measure it, we go to the measure tab and start from that point to that point. So we will find that the suspended ceiling has a height of 400 millimeter or 40 centimeter. Now let's go back to our drawing. And then we need to draw a duct, so we go to the duct. And here you can see its width is 500 millimeter and its height is 500 millimeter. So we can change its height to be, for example, 160 millimeter. And then we draw it from that position to that position, for example, and press escape. And now let's access our section. Here, this is our duct that we have just created. We can increase its offset. So if I press on the up arrow, here we rise it up. And at this condition, you can see we have no problem. We can set our duct at any position that we need, as we have a free upper space and a free lower space. This is because its height here is 160 millimeter, while the total height that we have is 40 millimeter. But suppose we have another duct that will intersect with that first duct. So if we go back to our ceiling, we can insert another duct. So if I press in duct and make another one that interferes with that first duct to be at this position, for example, so you can see it goes with a perpendicular way with respect to the first duct we have. And now let's make the height of the second duct to be, for example, 250 millimeter. That's it. And then we can go back to our section. And to express our second duct, we can go to the details little and make it to be fine. So that's the second duct. You can see it goes lower than the suspended ceiling, but we need this second duct and this first duct, both of them to be included inside our suspended ceiling. So let's delete the dimension, for example. Here we select it and delete it. And then we can rise that duct up. So we press on the up arrow on the keyboard. So this is the maximum limit that we can insert our duct at which. And for the second duct, we can increase its up also to include it inside our suspended ceiling. So you can see we have a problem here. If we need to make the second duct to be included totally inside our suspended ceiling, so this is the upper surface of the suspended ceiling, and at that condition we have the lower duct to be included exactly in our ceiling. But the problem now is that there is an interference between this vertical duct and this horizontal duct. And in our case here, or in some practical cases that you may face, there is no way to change the direction of that duct, so it intersects with that duct, and we can see that well in the 3D model. So if we go to the project browser and select the second ceiling again, and then we can select the duct, and here control and the duct, and then we press on the selection box. So those are the two ducts that we have, and here we can see them well. So if we make them at that position, you can see this dark blue area is the intersecting area between the two ducts. And for that, we need to find a solution that will separate those two ducts from each other to make it able for the two ducts to pass through our ceiling. And if we need to analyze that problem, we will find that the total height of the two ducts is 160 millimeter for the upper duct and 250 millimeter for the lower duct. So the total height is 410 millimeter, while the total height of the suspended ceiling, as we have measured before, was 400 millimeter only. So the suspended ceiling now has no sufficient height to carry the two ducts at the same time. And to solve that problem, we have two ways for doing so. The first way is to change the dimension of one duct of them while keeping the cross-sectional area of that duct to be constant. So we can try to change the dimensions of that lower duct, for example. And if we go to this right dimension, we will find that this is the duct. If we select it, it has the width of 500 millimeter and the height of 250 millimeter. But if we change it to decrease the height, for example, to be only 200 millimeter, so if we decrease its vertical height to be only 200 millimeter, here we can make that one to be 200, and if we increase its width to be 570 millimeter instead of 500, this is to compensate the decrease in the height. So at that condition, we will find that we have the cross-sectional area constant, so the airflow inside it will be a constant value, and at the same time we have decreased the height, so we provide more free distance for the two ducts to be installed at each other. So you can see here, this is the suspended ceiling, this is the upper surface of the suspended ceiling, and this is the upper surface here. This one is the upper surface of the concrete ceiling. So if we increase the offset distance of that duct, for example, we press on the down arrow on the keyboard, you can see we have also a distance between it and the suspended ceiling, which means that we can install it exactly on the suspended ceiling, and also this one we can decrease it. So by that way, it's included inside the ceiling we have, and also we have a distance, or we have a free distance between that horizontal duct and that vertical duct. So by that way, by decreasing the height of each of the two ducts, we can provide the distance that we need to install our ducts. But when you are changing the dimensions of the duct line, that one for example, or if you decided to change the dimensions of that duct also, you must take into account some notes, which is that the aspect ratio of the new dimensions of the duct to be in the acceptable range, which is to be less than 4. And as we learned in the part 1 of our course, the aspect ratio is the ratio between the larger dimension and the smaller dimension. And we can check that by the calculator. So the new dimensions are 570 and it's over 200. So it's 2.8, which is exactly less than 4. So the aspect ratio of the new dimensions is in the acceptable range. Also, the second note to take into account is that the pressure losses and the air losses inside our duct after making those modifications must be in the acceptable range. And finally, the cross-sectional area of the new resized duct shouldn't be less than the cross-sectional area of the old duct as we said before. So if we achieve those conditions, we can resize our duct to provide additional length in the vertical direction. Very good. So that's about our first solution. Now let's go back to the plan view. And also let's make the dimensions of that horizontal duct to return back to its original values, which was 500 times 250. And here the second solution is that there is a trick that we make to reduce the height of one duct of them or the two ducts at the same time and the intersecting zone between them. So we are reducing the height only at the intersecting zone while the duct remains with its constant dimensions at the rest of its length. So what we will do is just to decrease the height of that part and keeping its width constant also. And at that condition, the scenario that will happen is that this length, for example, will have a smaller height, while this length and this one will have the same height. And this means that the reduced duct will be connected with the two ducts and the two sides with a duct reducer. But you know, this method has some conditions that you must achieve to end up with the right design. The first condition is that the length of the reduced duct at the intersecting part must be larger than 3000 millimeter. So this area that we will intersect must have a length that is larger or equal to 30 centimeter. And also the second condition is that the declination angle of the reducer mustn't be larger than 15 degree. So it must be 15 degree or lower than that. And this is to allow the airflow through the reducer to go easily as much as possible and not to have any disturbance inside the reduced height duct or inside the duct reducer. And finally, the last condition and the most important one is that the height of the reduced duct mustn't be less than 80% of the old height. Or in other words, the reduced height mustn't exceed 20% of the old height. Now let's see how to perform those concepts practically. So we will work on that horizontal duct as we said, and what we will do is from the modify tab we will go to this command which is to split the element, and then we will cut, for example, from that point here, and then cut from that point and press escape to end the command. And now we will select this trimmed part and delete it. And then you can see we have two extended parts here that we don't need also. So we select that one and delete it. And we select that one also, here that one, and delete it. So you can see this duct has the original dimensions, which is the width of 500 and the height of 250. So we need the new duct to have a height that is 80% of the old height, which is 80% of 250. So the 80% of 250 is 200 only. And for that, we will go to the system and insert another duct. And this duct at this condition will have a height of only 200. This is the 80%. And this is the first condition that we took about. And let's start making the duct from that point, for example, to that point, and then we press on escape. And now let's see that construction from the elevation side of view, for example, to see what's going on well. Here we go to that section and press a double click on it. And as you see, those are the two parts that we have with the original dimensions, and this is the reduced duct, so we need to connect between that one and those two ones. But at first we need to make the height of that duct on its offset to be the same that one and that one, and for that we will align its face or its down surface with the down surface of that duct and the down surface of that duct. And to do so, we easily select it and go to the Align tab, and we don't need to save now, and select that surface to be the initial line, and select that second surface to be the second line, and that's it. Now what we will do easily to connect that duct to that one and that one to that one is easily to select it, and then we drag it until we see that blue line, so we end it. As you see, we have made the reducer or the duct reducer very well, and we can make it at that part, for example. Here we go until we see that dark blue line, and that's it. So as we said, the first condition has been achieved, which means that the height of the reduced part is 80% of the total height of the old duct or the original duct. And now for the second condition, we need to check it, which is that the length of that reduced part is in smaller than 300 millimeter. And for that, we use the measure option and start measuring from that point to that point. And that's it. You can see it's 1.8 meter, which is about 2 meter, so it's very larger than 30 centimeter. And also for the third condition, which is related to the reducer angle, if we select that reducer and go to its properties, we will find that its declination angle is exactly 15 degrees. And if it was generated automatically to P30 or 45, we must set it back to P15 degree. Very good. Here, this angle is equal to this angle, and our conditions has been achieved. So by that way, we managed to provide a distance at which we can install the two ducts at the same intersection area. So this is the upper ceiling surface, and we have a distance between it, or an offset distance between it and the lower surface of the duct. And also for the upper surface, we will find that we have a distance here from the upper concrete ceiling and the upper duct. And also we have a distance between that vertical duct and that horizontal duct. Very good. Now we can see that also in the 3D model. So if I close that tab and I press on that selection box to see them in 3 dimensions, as you see, those are the two ducts that we have. This is the reducer, and this is the duct at the original size, and this is the duct at the reduced size. And when we see it from the front, we will find that here this is our duct, and this is the offset distance. Here we have 3 offset distances, one at the upper and one between the two ducts, and one at the lower side. Very good. Now let's close that. But we can also perform that duct reduction at the two ducts at the same time. This is in case of we cannot afford the required reduction height from only one duct. So suppose we need to decrease the ducts with a height of 20 centimeter to be able to include the two ducts inside the suspended ceiling. So our case now need 20 centimeter as a required height. But the 20% of reduction of the duct height gives us only 10 centimeter from each duct. So at that condition, we make the reduction process from the two ducts together to get the total height as we need. And for that, I have prepared that construction for you to understand it well. So when we go to the first ceiling, here you can see this is the case that I told you about. And when I select that part to see it in the 3D form, and press on the selection box, and now let's see it from another dimension. Here, let's rotate it. As you see, those are the two ducts that we have, and this is the reduced part from the upper duct, and this is the reduced part from the lower duct, and this is the reducer for the lower duct and a reducer for the upper duct. So what we want to say is that you can perform that operation for both of the ducts, not only one duct. And this is according to our need. So according to our need, we perform the required design. Very good. Now let's go back. And finally, the last note we have is that we can detect the required cross-sectional area of the duct by the equal friction method and the equal velocity method, exactly as we have discussed on the previous part of our course. So we can make those calculations automatically by the Revit. And for that, we can select the whole system we have, and then we press on filter. So we check none and then select the ducts as we need the ducts only, and then we press on apply and OK. And after that, we don't need those ducts, so we press on shift and select them to deselect them. That's it. Or to deselect anything, we press on shift and select it. Also, we need that fitting to be included, and that fitting, and also that fitting. And then you can see we have this option appears here, which is the duct pipe sizing. So we press on it, and then it asks us for the method by which we need to make that sizing process. Here we have the equal friction method and the velocity method and the friction method. So we will select the equal friction. And here the program supposes for us a default value for the friction. According to it, it will calculate the required sizing of the ducts. So we will set it to its default value, and we press on OK. And as you see, the program tells us that there is a problem on the fitting here. So it's not important, but the important thing now is that you can see this duct size has been increased, and this is logically because it will carry the total CFM value for the total ducts that we have, while this duct or this branched duct will carry only the CFM of that diffuser, so it has a smaller size, and this duct, for example, has the same size of that duct because they will carry the same CFM, and also the same thing for that duct. Very good. So that's about the duct sizing method and the Revit software. Here we can press and cancel, and that's it. So that's about this tutorial. Hope that's it right now. Thank you for watching and see you next tutorials.